welcome to lecture 2. I'm going to start the video like I haven't been talking for 10 minutes. All right. So the first question from the reading was this term from the book. So the surface. So what does anybody remember what was going on when the author talked about this equation? What is this at df surface? I didn't just jump right into talking, so I can set this back up again. So the context for this, we had a little element of fluid, and we want to know what the forces on it are on it. So we start off by asking df. This little d means a tiny little quantity. And how many of you have had thermo so far? Okay, a couple of you have seen thermo. A bunch of you have not seen thermo, and that's okay. I don't need you to have seen thermo. But when you're taking thermodynamics, du and dq, d whatever is a tiny little element of something. And it's kind of like a derivative, but kind of not. And thermodynamics and the way we deal with these differentials is one of the things that drives mathematicians nuts, because we are much sloppier than we should be. Because I'll just take this thing, which is a quantity, and divide it by another tiny quantity and pretend I have a derivative. That's not how derivatives actually work. But we do it anyway because we're physicists, and we can just make it work. So okay, df is a tiny little quantity of f. So I've got some fluid, like the air in the room. Got a little parcel of gas, and I want to know what the forces are on it in each direction. So the way I did it was I just said force. I did the bit with the acceleration, which is complicated and confusing. We don't need that for now. We know there's an acceleration. We just want to know what the force is. The net force, I just said it's grad p. There's a 1 over rho that shows up there, and that's because it's only velocity on the left-hand side. So the 1 over rho goes away. Will show up again in a second. I just said that f is grad p. I just kind of stated that the other day. Because the force on a little parcel is just the difference in forces along the sides. Let's do that a little bit more rigorously. So, and let's not make this a square. Let's make our little element a square, or a circle. Let's make our little element a square. Let's make our little element big so you can see it. Okay, this is infinitesimal, large for now. Let's think about what dfi is. What do I mean by dfi? So df with a vector on top is a vector. dfi, also a vector. Completely and totally the same. Just a different way of writing it. The reason that I write it like this is because I can also think about this as one of the components of the vector. This one, I. This is df x, df y, and df z. So I can think about this as the whole vector, or I can think about it as each one of the components that I need to deal with at this time. The two thinkings are the same, and that freedom makes things easier and harder at the same time. So dfi is one component, and it is equal to pij dsj. So what do the repeated indices tell me about this? Somebody yell something. What do repeated indices do?
They're summed over.
They sum. Okay, so we're summing over the second index. So, but this is a free index too. So let's pick one. So for x, dfx equals pxj dsj. And this is a sum over 3 items. Does that make sense? So I'm just picking one. This is equal to, we're summing pxx dsx plus pxy dsy plus pxz dsz. What the hell is pxx? What is pxx? That doesn't make any sense. This is the x pressure along the x face. This is the x pressure along the y face. This is the x pressure along the z face. So we have a pressure in each one of these faces, And I have a component going in this direction, and I have a component going in this direction, and a component going in this direction for the pressure tensor. Does that make sense? So my tensor, my pressure tensor at this face, so Pxx, there's a component of the pressure tensor in this direction. There's a component of the pressure tensor in this direction too. That component is going to become clear why I need this component in a minute. For the gas pressure, it's 0, because the gas pressure just pushes in one direction. The gas pressure is isotropic. Does that make sense? So I have this tensor, and its direction and phase. Now, it's symmetric, so you can switch those two and think about it in the other order. Not all pressure tensors are symmetric. If I have a magnetic field with something complicated in it, my pressure tensor is going to have a magnetic field and some directions, and it's going to be really gnarly. So for gas pressure that you're most used to, calling it a tensor seems a little counterintuitive, but it'll be useful to do it this way later. So I have this tensor, Pij, and it's the pressure along I in the J phase. So this is just a little differential. What is the total pressure on my say little parcel? Let's just talk about this. The total force, dF on the surface, equals the integral along the surface of Pij dsj. I'm sorry, I didn't say out loud what S is. What do you think S is? Somebody make up something. Surface. This is surface area. It's a little element of surface area. So the total net force on the surface in the I direction, you know, I have an unmatched index here on my pressure index. So this is a vector too, not a tensor anymore. We contracted this index. So we took a square thing and we multiplied by a vector thing and we get a vector thing. So the surface in the I direction is the pressure in the X direction on all the faces. Does that make sense? Now, Gauss's law, one of these days I'm going to disassemble this board and make it easier to pull, but I have not done that yet. Okay, so F on the surface is the integral along the surface of Pij dsj. That's what I just wrote at the bottom of the last one. Now, surface integrals are a headache to do because I got to go figure out where the surface is on the whole thing. That's a hassle. Easier is dealing with the volume integral. So this is a surface integral. How do I turn a surface integral into a volume integral? This is a running theme. There's somebody's law. Starts with a G, and you got to take a derivative.
Gauss divergence.
Was that?
Gauss divergence.
Yeah, use the divergence theorem. So we use the divergence theorem. Here we have a surface integral. How do I turn this into a volume integral? This becomes d by dx j Pij dv. Okay. That's a thing that you've seen a bunch of times, but maybe you didn't follow. What is this? dxj, d by dxj. This is nabla. So another way that I could have written this is I could have said the integral of div Pij. Now I'm mixing notations. This should have two index thing there, dv. So now, I've gone from having my integrator, this is a volume element, or this is a surface area element. It's a vector. It's got a component. It's got a direction because it's the area element. This one has a volume element. So, but I'm integrating the derivative. So now, F surface is equal to the integral. Oh, I missed a minus sign in all of this. Sorry. It's too focused on the vector calculus. So the surface force is the integral of the divergence of the pressure tensor. Or, since my pressure is not a tensor, it's a scalar, it's the gradient of the pressure. Wait, does that make sense? Yes, no, kind of confused. Everybody's happy? So, this bit here maybe I'm going to mark that word over here. Middle, so I don't cover up my other stuff. This one slides better than that. Yeah, that one slides. I'll use that one more. So, okay. So, this D surface is this kind of complicated thing. D tensor, dx tensor. This d by dxj, this is a vector. This is another way to write the nabla gradient operator. A Pij is a tensor. Taking the derivative of a tensor gives you a, taking the contraction of a nabla with a tensor gives you a vector. And that gives you the total surface, or the total force on all of the surface. That makes sense? It makes more sense when you put your hands on it and do it yourself. Question 2. So question 2 was, how's he rated? dq equals du plus p dv. And the question was, where does this come from? It doesn't come from anywhere. This is one of those equations that we magic. You just write this one down by saying, I'm pretty sure this has to be true. This is the first law of thermodynamics. I'm not going to spend a ton of time on it, and I'm not going to ask you to have to manipulate this at all. But now we can talk about it and we can see it a little bit. So I'm going to spend a minute on this, and I'll derive the internal energy equation as we go. The internal energy equation is not one that is as constitutive as, it's not as important as Navier-Stokes or continuity. It's not that it's not as important, it's that the energy is always something, a lot of times it's something that you have a different handle on, so you can kind of get rid of it. But we'll have to deal with it some of the time. Some of the time we can ignore it. So dq, one of you who has taken thermo, what's dq? Heat. So the dq is the heat flux. So dq is a tiny little element of heat. du is what? du is internal energy. And pdv is what? This is the work. So you have a gas with some pressure. If you change its volume, you have to do work. If you have internal energy is, for an ideal gas, just the temperature. For something else, it might be some configuration energy or whatever. Internal energy is all of the microscopic energy. And dq is the heat that comes in and out of a surface. So what the first law says is I have a box, and it has some internal energy, U. It's just a thing that it has, is internal energy. It also has a pressure and a density, or a volume. In thermo, you always deal with volume, and here we'll deal with density, which is 1 over volume, which has interesting consequences. So the gas has some quantities, and if there's a heat flux through it, dq, through the side, then I'm going to change P and U, or V. I'm going to change some of these quantities to account for the heat flux. And depending on my boundary condition, I can fix one or the other. If I fix the temperature, then I can fix this, and then all of the heat flux goes into work. Or if I fix the volume, like with a rigid bottle, then I can't do any work, and all of the energy change goes into internal energy. So if I have a rigid cylinder and I start to heat it, I'm not going to do work on the gas. It's just the internal energy is going to go up until the bottle fails, and then we'll do work on the gas. And then the work will do gas on the environment as it expands. So this is something that will come up again, but I'm not going to ask you to know that at any point. So what do we do with the internal energy? So we could talk about the internal energy of the gas. So any particular gas has a density, a velocity, which is a vector, and an internal energy, or pressure, or temperature. You can deal with any of those independently. They're equivalent. So we start with dq equals du plus p dv. V is a difficult quantity because that's really about the edge of the quantity, whereas rho is about whatever the particles are doing microscopically. So I'm not going to talk about V, I'm going to talk about rho, but it's a V here, so what am I going to use is I'm going to use 1 over rho. So V is 1 over rho. Oh, I got a little mass element here, so I got to divide everything by the mass. So we've got to rewrite this. Now it's going to be dq. Little q is now the energy per unit mass. This is the total energy. This is the energy per unit mass. Equals d, we'll call this epsilon, plus p d 1 over rho. All I did was divide by the mass and rewrite the volume. That doesn't do me a lot of good. Here's the physics stunt. I'm just going to divide everything by dt. Really, a derivative is a limit of little things, but we skip that because whatever. And that gives us dq dt. And this quantity ultimately is the most dependent on the problem that you've got, because it's going to be, can my function radiate? Is it heated? Is it like, what am I doing to this thing? dq is going to come from the boundary conditions of the problem most of the time. Equals dE dt plus p d1 over rho dt. And that's not a great quantity to deal with. Let's simplify that. D by dt of 1 over rho is equal to what? Chain rule. So I get a minus sign because it's 1 over rho. I get a rho squared because I derivative that. I differentiate 1 over x. The derivative of 1 over x is 1 over x squared times d rho dt. Oops. 1 over rho squared. Sorry. I can't calculus correctly all the time. And we got what d rho dt is. Oh, I'm sorry. Okay. One of the running themes in this class is that a partial derivative or a full derivative? It makes a difference. This is a full derivative. Because we started here, this is a whole quantity, this is a whole little bit of heat, and this is a whole little bit of internal energy, and this is a whole little bit of volume. So when we differentiate, we're differentiating by a whole little bit of time. So these are whole derivatives, not partial derivatives. Well, when a partial derivative, you hold other stuff fixed. So d rho dt, let's talk about that. I got partial rho partial t plus div rho v equals 0, but I want full derivative d rho dt. So one of the, yeah, I'll do that on the side. Uh-oh. Trip over my cord. One of the things they like to do in the Geophysical Fluid Dynamics Institute is study fire, which is kind of awesome, and how wildfires spread. It's one of those, it's a topic that I really wish that I had time to work on. It seems super interesting. Oh yeah. Partial rho partial t plus div rho v equals 0. Now, you remember last time I did d rho dt. This is the full derivative. Rho depends on what? Rho depends on x, y, z, and time. So if I want the full derivative of this, I just got to partial all the stuff that it depends on. So this is partial rho partial t plus, I did this already, but I'm going to do it again, and you're going to do it again. This is a running theme. D rho dx, dx dt, plus, somebody help me out, what comes next? D rho d what? y d y dt. And then the last one is what?
d rho dz dz dt.
dt. Yay. Okay, and what's dx dt? What is in x? There's vx, vy, and vz. And this, let's get a different color. This, and this are all nabla rho. Do you see that? So this whole thing, I got this pair of stuff. This is equal to plus v dot grad. It's important that the parentheses are around v and grad so that you don't screw it up. It's real easy to screw up this operator, especially when we get to the velocity. It's just rho grad v. So d rho dt is partial rho partial t plus v dot grad rho and that's all I need to say. If I want to get an equation for this, what does this equal? Well, I know what d rho dt is. D rho dt plus div rho v equals 0. I can expand this with product rule. So then I get d rho dt plus rho div v plus v dot grad rho equals 0. Does everybody follow that? Yeah.
Kind of hard to read. What?
Oh yeah, when it gets down to the bottom. So this is v dot grad rho equals 0. So I've got d rho dt, I got a rho times div v and a v dot grad rho. So it's a lot like that other equation that we had. But we've expanded this out, so now we see that the time derivative is this, and this is what the time derivative is equal to. Would it follow? So this is true. I can also say that d rho dt plus rho div v equals 0. So this is another way to write the same equation. This way we see it's like a conservation law, and this way we see what happens to density as it goes along. So density is affected by div v, the velocity divergence. This is a fact that is important in life for some of us. So I'll move this back over here. What were we doing? We were doing the internal energy, and we needed d rho dt, and we got it. So now, so this equals minus 1 over rho div v, because d rho dt is just rho div v. Everybody follow that? So now my internal energy equation states dE dt plus P over rho div v equals dq dt. And dq dt we have to find something else out for. We'll talk about that in a second. But this is how the internal energy propagates around. One of the big differences between internal energy and density is you can't make more density, but you can make more internal energy by doing work on it. So it's another conserved quantity. It's useful to write this in a conserved form the way we did with density, and I'll make you do that. I think the book does that in this chapter, and I'm going to make you do it for homework because it's good for you and super tedious, but really good for you. Okay, internal energy. Let's see. Oh, the last question. So, the last question I got from the reading So now we have a new and fundamental equation that I'm going to write over here for now. Because we'll need it sometimes. d epsilon dt plus p over rho div v equals dq dt. And he turns that into a conductivity, which I can probably do now. So dq dt is what? Well, a little element of Q flows when there's a gradient in temperature, K grad T. Now, here's another short aside. In the book, he quotes that K goes like some number times T to the 5 halves. He just states this. What he does is he redirects you to the second half of the book where he derives it. The derivation of this is a headache, and I'll do it in a couple of weeks, but it comes from plasma physics, so we have to talk about ions and electrons smashing into each other. So this T to the 5 halves comes from the electron mobility, and we'll derive it a little bit later. But we want to know that how does this affect our blob. So across this interface, the flux is K grad T. So if I want to know what the total heat flux is, then I have to have a surface integral of K grad T dA. Now we don't like surface integrals because they're a headache, so how do I turn this into a volume integral? We've done this already. Whose theorem is it? It's Gauss's theorem. So my surface integral turns into a volume integral of div K grad T dA. Oh, no, not dA. What am I integrating over here? Volume. dV. d volume. So then I can just drop that, since all of that is a volume integral as well, I can just drop that, and K cubed can dq dt equals minus div K grad T. So if K is a function of space, then this function is hard to deal with. I'm going to spend 30 seconds on something that's easier to deal with. So I got dE dt plus P over rho div V equals, what do we say, minus grad K grad T. One of these are vectors. There's a dot product that needs to be in here. Okay, T is a scalar. That's a vector, so this quantity is a vector. This quantity is a vector. This needs to be a dot product here because this is a vector. And this side is a scalar. I'm pretty happy taking nabla of a vector because that's 3 equations. But this is a scalar, so it needs to be a dot product. So if K, the thermal conductivity, is not a function of space or anything, if it's a constant, which it often is, then I can take this outside and I'm left with minus K del squared T. And if velocity is 0 or small, which it often is, like in this room, the velocity of the air isn't very large, then I can eliminate this other term, and I get d epsilon dt equals K del squared T. Does anybody know what this equation is called? Have you guys ever seen something like this before?
The wave equation?
This is not a wave equation. Good, this is a good guess, though. The wave equation wants a second derivative on the time. This one is the diffusion equation. So until you've seen them like a million times, it's hard to keep them all straight. We'll get to wave equations. This one is simpler because it's nice. It's fully characterized. We understand exactly how, given any initial disturbance, how this equation will behave. Give me any initial t, and I will tell you how this evolves. which is useful. What happens is if you start off with a delta function, say I just have a little bit of heat, it diffuses and spreads outwards in a diffusive pattern. So it kind of slowly smooths outwards. It kind of oozes outwards. This is like if you've got, you know, if you put a candle in a room, it'll slowly heat the room up as the heat diffuses out away from the candle. So the diffusion equation is when there's heat but no velocity. And it's a useful equation. So this del squared, we have one over here, this del squared V. I'm just pointing that out right now. That'll come up later. So we'll talk more about diffusion later, but it comes really quickly from the internal energy equation. Cool. I'm going to do. Oh, sorry. I'm staring at the clock.
Oh. Got anxiety.
Yeah. No, I'm going to do. I'm trying to decide if I'm going to go through Kelvin's or Bernoulli first. I think I'm going to do Kelvin's vorticity theorem before I do Bernoulli because it might take me the whole time. And Bernoulli is pretty straightforward, but the vorticity theorem is confusing. So before I do the vorticity theorem, I've got to define the vorticity. This is one of the most important quantities in fluid dynamics. And it's really simple. Omega is the curl of V. So what does curl do? Curl is spinning around. Curl is rotatingness. So omega is like the rotation of the fluid. It's not exactly, but it's like the rotation. Think about it like the rotation of the fluid. So if you remember from the video from the first day, we had this ring of bubbles. That ring is rotating in this direction. It's like inward, inside, outward. Oh, you weren't here the first day. I'll show it to you at some point. I might have shown it before because it's hilarious. There's this ring of bubbles and a jellyfish gets sucked into it. It's really hilarious. And I would feel bad for the jellyfish, but I'm pretty sure they don't have feelings.
That stings.
Yeah. Thank you. Okay, so omega, how do we deal with omega? You know that rotation is important. Angular momentum is one of those conserved quantities, right? If something starts spinning around, it'll stay spinning around forever until something stops it. That's why we get hurricanes. That's why you get tornadoes. That's why all kinds of stuff. Vorticity is, for the most part, a conserved quantity. It's not a conserved quantity in the same way that mass is a conserved quantity. And I'll talk about how do you deal with general conserved quantities in a little bit. Vorticity is not quite conserved. It's kind of conserved. Mass is conserved because if I draw a little surface, I know whatever comes out of my surface is the change in the mass. So I can see what happens. And I'm not going to make any new mass because this is a non-relativistic course. But vorticity, you can make vorticity, and it's not conserved in the same way. It's conserved in this weird thing in areas. So vorticity winds up arranging itself in rope-like structures. There isn't anything. I stare at fluids, and this is what it does. This is what they do. Fluid vorticity winds up being in rope-like structures. I can't prove that, and if I could, I would be super famous. Well, you can kind of wave your hands and get at it, but where is the vorticity in space is a very complicated question. But it winds up being in rope-like structures because you start something spinning, and the whole thing is going to spin, right? I can start this spinning. It's got an end, so that makes sense. But if this is in a continuum, if I just imagine a little bottle of fluid here. If I start a little ball rotating this way, it's going to spin up and make the whole line of material rotate. So vorticity lives in strands. And if I take a bundle of lines of vorticity, and I draw a surface, let me do that better. My surface goes behind my vorticity. Then the vorticity that goes through this surface is conserved. So vorticity is pretty much conserved. That's really the primary takeaway. But first we need an equation for vorticity. So how do you think we're going to get one? I got an equation for velocity. I'll just take the curl of it. And then I've got an equation for vorticity. So let's see. dv dt plus v dot grad v equals minus 1 over rho grad p, and we're going to skip the viscosity term for now. Okay, I'm going to take the curl of this. And the first one is easy because nabla and the time derivative commute. So I get partial omega partial t plus this term. Let's skip this term for a second. This term, curl of the gradient of something is what? Zero. Curl of the gradient is 0. That's a super handy thing. The curl of the gradient of something is 0. This term, okay, this term is a headache, and now I realize that I can't do it off the top of my head like I've done everything else. I gotta remember this identity, because I mess up this identity if I don't write it down. So in the back of the book, there is a bunch of vector identities. You should memorize them. That's a total lie. You should know where that list of vector identities is and be familiar with them. If you happen to memorize them, sweet. But I have not yet, and I've been doing this for a long time. So v dot grad equals 1/2 div v dot v minus v cross curl cross v. It's an identity you look up. So the identity states the identity is on what grad a dot v is, and it's not product rule doesn't distribute over the dot product when things are vectors the way you want them to. So there's a horrible vector identity. Actually, let's put it up over here. Div a dot b is a cross curl b. You don't have to write this down, it's in the book. Plus b cross curl a plus a dot grad b plus b dot grad a. So how do you see that? I don't remember. At one point in time, I understood where that came from, but I don't remember. I don't remember right now. So you got to write this down with the components, and then don't screw up your tensor calculus. So we use this identity to rewrite v dot grad v, this term, as 1/2 div v dot v minus v cross curl omega, or curl v cross curl v. I'm jumping the gun. Oh, sorry. I don't get to curl this yet. I don't get to throw this out yet, because this isn't the gradient of a thing. It's 1 over rho times the gradient of a thing. I'm not done with this term yet. Sorry, I jumped the gun. So d omega dt minus del cross v cross. This is v cross del cross v. This is v cross omega equals. So I'm going to take curl of 1 over rho grad p, which is equal to 1 over rho squared grad rho cross grad p equals grad rho cross grad p. Okay, I'm going to write this one down too. So we started with the Euler's equation. We took the curl. We threw in a derivative. And we get a vorticity equation. d omega dt minus curl of v cross omega equals 1 over rho squared grad rho cross grad p. We take the curl. Where did this term go? I didn't write this term down over there. Why not? Because it's 0. Why is it 0?
The gradient of
Curl gradient is 0. Okay, so now I've got this equation. d omega dt minus curl of omega of v cross omega equals 1 over rho squared grad rho cross grad p. Okay, let's talk about the last term again. I do get to throw it out. I just forgot why when I was writing it down. Why do I get to throw that out? Grad p cross grad rho. Oh, it's the other way around. Grad p cross grad rho. Well, p equals rho t times some number. PV equals nRT. I put the v on the other side. N over v is density. There's a mass and a k and some other numbers, but I don't care about those guys. If the temperature is constant, this is the easiest way to see it. If the temperature is roughly constant, then this is equal to grad p cross grad p times some numbers that I don't care about. And what's that? A vector cross itself is what?
0.
0. So this term goes away. In many cases, this term goes away. This is called the baroclinic term. It's a way to produce vorticity. It will turn out that it is a way to produce magnetic fields too, because it turns out the vorticity equation and the equation for magnetic fields are identical, which is neat. So you can produce magnetic fields with similar kinds of stunts. It requires violence, but because you got to rip the electrons off the protons and have some charge separations, but you can do it. You can make magnetic fields just by how this stuff is arranged. So the last term we get will go away. Let's talk about this vorticity equation. Okay. d omega dt minus curl of v cross omega. Okay, now with a lot of these triple products, it's really important you keep in mind where the parentheses are, because the order of operations matter. This is not curl omega cross omega, or curl of v cross omega. That's 0. Let's talk about this term for a second. Let's talk about, so what we want to know is, or what Kelvin sorted out, and we will go through his derivation, is how is this conserved? Oh, equals 0. Sorry, I didn't write a whole sentence there. So if I take a surface, so you remember Gauss's theorem changes volume things to surface things with the divergence. Stokes' theorem turns curly things into line integrals with the curl. Turns flat things into 2D things into 1D things with the curl. And 2D things into 3D things with the divergence. So Stokes, this is a curl, so we're going to need to use Stokes. So I'm going to have a surface S. So this is a surface S. And my stuff is all swirling around. And I'll think about, this is omega. It's a vector. Okay, omega going up that way means the velocity is, okay, if I have omega doing this, what is the velocity doing? Yeah, I see you're all doing your right-hand rule thing, right? So it's going to go like this. That's perfect. So the velocity is swirling around. Now, there's a difference between bulk rotation and vorticity. If I have if I have a bucket of water and I put it on a turntable and I let it spin and I let that go until all the water is moving in a solid body with the turntable, its vorticity is 0 even though it's rotating. So vorticity is about the local curvature. So it's a little different than rotation, but it is the rotatingness. Okay. So I have these vectors of omega, and really this is stuff that's spinning around like this, but that's okay. And I have this surface. What happens as I pull this surface over this way? What happens when I squish it? What happens if I squeeze it out, if I expand it a little bit? The vorticity is conserved, and d omega times a dt equals 0. Where a is the surface area. Okay, this isn't general enough. We'll write a better equation, but this is the way to think about it. Vorticity times area, the time derivative of that is 0. So if I make the area smaller, vorticity goes up. If I make the area bigger, vorticity goes down. This is just like when you were in 2049 or 2048, I think, and you had ice skaters spinning around on her foot and then pulls her arms in and she spins up, same thing. But this is now we're going to do it in the continuum limit. So this is just conservation of angular momentum. But we got to do it with continuous fluids. So we'll do that. So let's write this down. Okay, I'm going to put quotes around this because it's not really true. This is true by like waving your hands around it. What do I actually mean by this? Omega times A is the integral of along the surface of omega dot dA. And we want to know what d by dt of this is. And let's see. I have all of these notes in the margins because when I first taught out of this book, I just taught straight out of the book and all my notes are in it. So if I lose this book, I'll be super sad. It's like half of my thoughts about this material are in here. Is I going somewhere else? No. Okay. So d by dt of the integral of omega dot dA. I'm going to use product rule because I'm multiplying things together. Multiplying omega and dA together, so I got to use a product rule. So this is equal to d by dt. Let's put this integral on the outside. We'll deal with that in a minute. D by dt of omega, I know what that is, plus omega d by dt of dA. Here's where the derivation gets confusing. So this part's easy. We'll come back to that in a second. This part is confusing. So I have a little surface area, and it shifts over to another little surface area. What is the time rate of change of this surface area? It's a weird sentence. I know what the time rate of change of my bank account is. It's a scalar, negative. I know what the time rate of change is, but this is a surface, so what's the time rate of change of a surface area? That's kind of a more complicated thing. The way we think about this is we draw a can around this object. So I have a surface, it goes to another surface, I just make that into a can. Maybe the can is not really a can, I don't need it to have any can properties. It's just easy to draw this way. So I have ds1, that's my surface area here. And I have ds2, that's my surface area here. Surface area elements are always outwards. And if I integrate a closed surface, I get 0. Think about it this way. Simplify it a little. If I add this vector and this vector, they cancel each other out. If I add this vector and this vector, they cancel each other out. So if I go around and I add up all the outward going vectors, I get 0. For every left, I have to have as much right, as long as it's a closed, nicely defined surface. So this isn't a fractal or something. This is a nice thing that you can take a derivative of. So the total surface area has to be 0 if you do this integral. So ds2 minus ds1, that's what we want, plus the surface area of the side equals 0, right? Where'd this minus sign come from? It's because they're pointing in opposite directions, because one is it's the outward normal. So so we just need to sort out what the size of the side is to get the difference. This is the part that I want, right? So I'll just get that, and we'll have what we want. So I want this divided by dt. So what's the size of the side? Here's some weird vector calculus stunts. Remember that if I have, so this vector, the side of the can is set by the velocity of the fluid. So that's v times delta t. That's how far it goes. And the area of this is going to be, if I call the edge of the circle dl, then the side is this. So the area of this little infinitesimal rectangle here is dl times v dt. What kind of times? Cross times. Cross times gives you an area. If I have two vectors and I cross them, the cross product gives me the area of the parallelepiped that they define. So the area here is dl cross v delta t. dl cross v, is that outwards? Did I do that right? No, I got that backwards. Why is that? Oh, because he read it with a minus sign. So he writes it with a minus sign and then adds backwards. So the size, the magnitude of the area is dl, the length on the edge, cross v dt. So we'll take a time derivative of that. My dt goes away. So ds, oh man, I changed variables on you. I'm sorry. I do that from time to time. I apologize. Keeps you on your toes. That way you've got to be paying attention. ds dt is equal to just, you got to add them all up, v cross dl. Okay. Yeah.
Are those partial derivatives?
That's a full derivative. It's a good question. S doesn't depend on anything other than t. S doesn't care about anything else. So we'll go back to here. We'll go back to here. This term, turns into the integral of omega dot v cross dl. Does that make sense? So my ds dt is just v cross dl. It's just the side of the can. Now there's a cool triple product stunt. If I've got a dot product and a cross product, if I advance them cyclically, I get the same quantity. So I can rewrite this. Let's get to the board. As where am I at? So now I'm looking at the integral of, sorry, let's start at the beginning. d by dt, omega dot ds, let's call it ds this time, equals the integral on s of d omega dt dot d plus, what were we left with? Omega, let's see, we had omega dot v cross dl, but by the triple product, I can rewrite that as omega cross v dot dl. But this is an integral over my things, so this becomes an integral over the surface. So there's another little integral in there that gets consumed by the bigger integral. We're left with d omega dt plus, oops, I skipped a step. And bear with me 1 second. I wrote it down really smooth right here. And when I'm done with this, then I'm real quick going to show you how Landau and Lifshitz does it, because they do it in a different way. Are you guys all familiar with the Landau and Lifshitz books? So if you're going on in physics, or maybe now, Landau and Lifshitz wrote this series of textbooks in the 50s, and they are some of the greatest texts on physics that have ever been written. They're really fantastic textbooks. You can get them for free on archive.org because they're out of copyright. So you can just go get these books, and they're magnificent. They're beautifully written. Some of them are incredibly hard to read because they're really dense. The mechanics book is only this thick. Your mechanics book is huge, right? Your mechanics book you can kill a bug with. The Landau and Lifshitz contains all the same information, but it's only this thick because you've got to derive everything yourself. It's a great book. The fluid dynamics book is much thicker and really worth having on your shelf if you wind up doing anything with fluid dynamics. Okay. Where I go? So I'm at the surface integral of I had d omega dt minus the line integral of omega cross b dot dl. This is the thing that I did, that I screwed up. This line integral turns into a surface area with the divergence. So this turns into the surface area of curl omega cross d. Oh, that's still a plus sign. Dot dA. Does that make sense? I don't like this derivation very much. I guess finding it confusing by the end. The Landau one is much tighter, as you'll see. So then I'm left with integral of d omega dt minus, I'm just going to change this, curl of v cross omega dA, and this is the vorticity equation. So this is 0 always for everything. I can do the same stunt, and he talks about this in the book. I can do the same stunt with the magnetic field, and I show that magnetic field is conserved in the same way. Magnetic flux is conserved in the same way. Okay, let's do it. Let's do this a better way that I don't screw up what I do it. So, and this will be it for the day. Okay. No, Lifshitz says the same thing. I got a surface S, bounded by a curve dl. I want to know what omega is. I've integrated on this. I want the time derivative of that. So d by dt of omega dot dA. Okay, same thing. Oh, actually, first, we're going to change this to a line integral. If I make this a line, and if I make this thing a line integral, what does it look like? You'll get good at this before the end of the semester, I promise. It's a surface integral now. Whose theorem takes surface integrals and turns them into line integrals around the edge? What's that? This is Stokes' theorem. So we use Stokes' theorem, and this turns into d by dt sorry, this is, let me do this again. This is curl of V. I got the curl of V on an area. How do I turn that into a line integral? The curl goes away. So I get the line integral of V dot dl. Same question. We're just going to do it with velocity instead, and it makes it a little bit tighter proof. One of the bits of the proof that we need before I actually get into it is we've got to talk about dv dt equals minus 1 over rho grad p. I'm going to skip a bit. If I define the enthalpy W as p over rho, have you guys, I have never seen enthalpy in my life. I saw enthalpy in hydro and it was kind of confusing. I'm super down with enthalpy. It's my favorite thing. Guys, that was a complete set. Some of you should raise your hands at some point in time. Okay, who has heard of enthalpy and is comfortable with it? All right, who has never heard of enthalpy and has no idea what that is? You can totally raise your hand. That's all right.
I know what it is, but I don't know any equations.
That's perfect. That's exactly what I'm looking for. So enthalpy is P times V. It is a weird quantity that you'll learn about when you get to hydro. And one of the reasons that we like it is it's P times V. So when I take a derivative of it, I get P dV, and then another term. So it is a combination. It is the internal energy. Enthalpy is a combination of internal energy plus the configuration energy. Another physicist might hate that I said that. It's not really an energy. So it's how much stuff is there, P, times V, how do you get it there? So if I have a little blob of hot gas, say I've got, something that got hot for some reason, it has energy because it has temperature. It has enthalpy because it has temperature and is in a certain volume. So we go through a couple not super complicated stuff, jumps, but you need thermal for it. And you get the dV dt equals minus grad enthalpy. This is very cool because that's a full derivative. We'll see why that's cool in a second. This is not a full derivative. This is a scalar times a derivative. But this one is a full derivative. Enthalpy is a little bit harder to deal with than pressure. It has more baggage, so we don't use, so it'll come up a lot. And sometimes I'll call it H. People are squishy about that. So enthalpy, the important bit about enthalpy is dV dt is minus grad enthalpy. And now, what did I write over here? Same thing. This is partial V partial T plus the other part of the time derivative. I just wrote a big D, so that's the full derivative. Is all this stuff. We ignored that, and this turns into the enthalpy. So I've got d by dt of v dot dl. So again, this is the integral of dv dt dot dl plus the integral of v dot dl dot ddl dt. So, okay, ddl, I kind of hate that, but I'm going to do it anyway. So let's start with this term. So this is, so now what are we doing? We're integrating, instead of integrating in vorticity across the surface, we're integrating velocity around the edge. We get to do that because of the fundamental theorem of calculus, or Stokes' law, however you want to call it. So we're going around a circle. So let's talk about this guy first. This is the integral dV dt is minus grad omega dl. Integral of a derivative is the thing at the endpoints. It's a circle. I go back to where I started. What is this integral? 0. Does everybody see that? So this is just omega, or no, not omega v, sorry. Grad v. No. W. This is why I call it H, because my W, so that's not an omega, that's a W. So this is the gradient of the enthalpy. This is the enthalpy at this point minus the enthalpy at this point, which is 0. So okay. Nice. Plus integral of v dot d, what's dl dt? That's just dv. That's just a velocity again. I've got the time rate of change of my element here. That's just the velocity. V dot dv equals, that's just 1/2 dv squared. That's a useful stunt. You follow that? If I take the derivative of v squared, I get 1/2 v times dv dt. So I'm just doing another little integral here. And again, I've got the integral of a full derivative at the endpoints. So what's this one? Also 0. And we're done. D by dt of omega dot dA is 0. That's more compact, I feel. I don't know if it's really any harder, but I like that as is a derivation better. There's another one that I might give you when we get to E&M that is more accurate and more complete and makes more sense, but is a lot harder. Okay, does anybody have any questions before we stop? Everybody happy? I put up a homework. It's due in a week. The first couple problems on the homework are kind of basic math questions. So I'm just doing, so those questions are just so that everybody's on the same page. So if you have questions with the first ones, come talk to me and we'll, the first couple. Other than that, it's a relatively straightforward homework set, as mine go. Talk to you guys soon.